First, let's review RLC circuits. RLC circuits in series. I have here a resistor. I have here a capacitor. And here a self-inductor, L. And here I have some kind of a voltage source. I call it E. And it could have various different natures, as we will see very shortly. Let's call this point B, A, C, D, back to A. The way I start these problems always, and there's nothing wrong with that, I assume at one moment in time that this is positive and this is negative. I assume that there is no charge anywhere on this system, on the capacitor, and so a current will start to flow after a while, I. That current will charge this side of the capacitor positive and this one negative, and it will return. If we look at the electric fields, there must be an electric field E here in this direction. There must be electric fields here in the capacitor, also in this direction, going from plus to minus. There is no electric field in the self-inductor because the self-inductor is made of superconducting wire, just as all these wires have no resistance. And inside the battery, the E field is opposing. It goes from plus to minus. I now apply Faraday's law, and I go around this closed loop circuit, and I attach to the closed loop an open surface. Closed loop integral, I attach to that a open surface. And the open surface is easy to see here, it's flat. It's not so easy to see here, we discussed that earlier. It is some staircase kind of a surface, I don't want to go into that anymore, but what is important is that the magnetic flux inside the solenoid penetrates this open surface n times if you have n windings. We hit that very hard last time. So here comes Faraday's law, the closed loop integral of E dot dl. I split that up in the integral in going from A to B, plus the integral in going from B to C through the resistor, plus the integral in going from C to D through the capacitor, plus the integral in going from D back to A through the self-inductor. And this now, according to Faraday's law, equals minus d dt of the magnetic flux through that open surface B dot dA. And it also equals minus di dt. We discussed that last time, so I will not go into that. Now, what is the integral in going through the battery? That is minus E. Notice I go against the electric field if I go around like this. Here I go with the electric field, so this plus IR. Here I go plus the electric field, so it is plus Q divided by C. And remember that Q is always the charge on the capacitor. Nothing else makes sense. Q is always, whenever I use Q, it's always the charge of the capacitor. And of course, there is equal amount of positive charge here as there is negative charge here. What is the integral of, this has to be, from B to A through the self-inductance? Well, that's 0, because there is no electric field in the self-inductance. Kirchhoff's law does not hold. The closed loop integral E dot dl is not 0, it's minus L di dt. The relation, by the way, between this QC and the current is I equals dq on the capacitor dt. That relates the current with the charge on the capacitor. Now I'm going to reorganize this a little bit. I may have to save this one because I may need it later. So using I equals plus dq dt, I find now that Q dot double dot plus R over L times Q dot plus Q over LC equals that EMF. That is the EMF which is the driver. It's the one that could have various natures. It could be zero. It's not necessary that there is an EMF. It could very well be that this is just short-circuited and that we start at some initial condition when the capacitor is charged, we throw a switch and some currents will begin to flow. So E could be zero. There's also a possibility that E is constant. We would call that a battery. And then there is the possibility, when we deal with alternating current, that E equals E0 times the cosine omega t. But of course any other function is possible. E could have this function, this profile as a function of time, or this one. We will only in 802 deal with these two, and I will first consider the first two. You can also write this one using I equals dq dt, that I double dot plus R divided by L times I dot plus I over LC equals dE dt, the derivative of this driving voltage, so to speak. Now if we first take the case that the EMF is zero, there is no EMF, or that it is constant, then what you are going to see is you're going to get into the circuit under certain conditions, and I will specify those conditions, an alternating current which will ultimately die out. And if you think about it a little bit, it's immediately obvious why it has to die out. We call this regime the regime of light damping, and I will only discuss this regime of light damping, damping, not danking, and I will specify what exactly I mean by that. I choose arbitrarily that I equals 0 when t equals 0. And when I do that, I find for a solution for a constant EMF, EMF could also be 0, equals I0 times e to the minus t over 2L divided by R times the sine of omega t. And the value 2L over R could be called tau, that is the decay constant, and you will see shortly what I mean by that decay constant. Omega is now entirely dictated by the various components L and C and R. We call this one, and you will see shortly why, we call this one omega 0 squared. Now omega has to be real, otherwise this would not have a solution. And that immediately tells you then what the conditions are for light damping. If 1 over LC is larger than R squared divided by 4L squared, which is a condition for a real value for omega, it is required that R be smaller than 2 times the L over C. That would then be the case that I am discussing today of light damping. If this is not the case, you get a different behavior which I will not discuss. What now will the current look like as a function of time? Well, here is I. We started at I equals 0, that was the initial condition. And this exponential decay is like an envelope that pinches the current off. It will make the current die down. The zero crossings are equally spaced. with a period t, which is 2 pi divided by omega. And this then is very closely the period t that I have here, and these periods t remain constant. And this curve here is this e to the minus, and this is then this exponent. So this is the envelope which squeezes down the current. There is a mechanical energy which is easy to see, and that may help you a little bit. If I have here a spring, and I have an object hanging on the spring with mass m, and I let it oscillate about this equilibrium position, then what you're going to see, if you damp the mass in a way that the frictional force opposes the velocity and is linearly proportional velocity, then you get exactly the similar kind of differential equation that we had before, except you don't see L, you don't see R's, you don't see C's, you see other symbols like M's and V's and whatever. I think you've seen them in 801. This kind of behavior is exactly the same. It is an oscillating bob, exponential decay, and when n goes through equilibrium, you have here all the energy in the bob in terms of kinetic energy, which is 1/2 m v max squared. But when the bob comes here to a halt, so v is 0, then you have all the energy in potential energy of the spring, which is 1/2 k x max squared. And of course this x max, here in this case you would have x here, this x max slowly decays in time. But what you see here is interesting. You see a sloshing back and forth between, on the one hand, all the energy in terms of kinetic energy, and then later everything in potential energy. And when you're anywhere in between, you have a combination of these two. Now in a similar way, with the RMC circuits, as the currents oscillate back and forth, there is a time that the capacitor has all the energy in form of electric energy. That is the situation when I equals 0. And the energy in the capacitor is then 1/2 Q0, and it's the maximum value possible, which decays with time. Everything is in electric energy, and the energy in L, magnetic energy, equals 0. Now then there comes a time that I reaches a maximum, which again dies out, the maximum decays, and then Q on the capacitor is 0, and then all the energy is in terms of magnetic energy. There's no electric energy, and that equals 1/2 Li, which is the maximum value squared. So also here you see a sloshing back and forth between two different kinds of energy. Magnetic energy, which at one moment in time is all in the inductor, a little later, a quarter of a oscillation later, everything is in terms of electric energy in the capacitor, and it keeps sloshing back and forth, similar to the oscillating spring.